Hi, this is Kaylee Champion, and this is Passive Potential Sensing in Cislunar Space Simulations using Nascap-2k and SPIS. So plasma is everywhere in space. In our solar system, this is mostly emitted from the sun through the flowing solar wind. This plasma is composed of negative electrons and positive ions. So when we put a spacecraft into plasma, it's impacted by those charged particles, resulting in several currents, as shown in this image here. Those currents then generate a potential on the surface of the spacecraft. And the magnitude of this potential is dependent on the ambient plasma parameters, whether or not the spacecraft is sunlit, the materials on the surface of the spacecraft, and even its geometry. So what can happen is if there are two nearby electrically disconnected surfaces on a spacecraft, they can charge different potentials and experience an electrostatic discharge between the surfaces. This can then fry electronics and has actually ended spacecraft missions before. Now, in addition to this, electrostatic discharges can be an issue during docking operations. If two spacecraft are charged differently as they go through their docking, once they're close enough together or they make contact, they can again experience an arc discharge, which can endanger the missions. In addition to electrostatic discharges, charged spacecraft also experience electrostatic forces and torques. Torques is particularly large during proximity operations. So this can cause the spacecraft to spin up, requiring extra fuel to account for this perturbation, which may or may not have been considered prior to the operations. Fortunately, we've been looking into novel touchless potential sensing concepts that will allow us to determine the potential of a nearby target to avoid electrostatic discharges and account for electrostatic forces and torques during proximity operations. Now, there are a couple of different methods for touchless potential sensing. I'll be focusing on passive potential sensing using electron emissions, so I'll just describe that here. But in this example, I've got a negative target and a positive servicer, which is the spacecraft that we are in control of. The target is being bombarded by ambient electrons and UV rays from the sun that then emit secondary electron and photoelectron emissions. These electrons are emitted with very low energies, and so they are repelled from and accelerated by the negative target, and then attracted to and also accelerated by the positive servicer. So when they arrive at the servicer, they have an energy about equal to the potential of the servicer minus the potential of the target. The servicer can read these electron emission energies, determine the difference in potentials, use existing technology to determine the potential of its own spacecraft, and we can finally infer the potential of the target. Now, we've mostly looked into touchless potential sensing in geosynchronous orbit. Here, there's highly energetic, pretty sparse plasma, but we are hoping to implement this around the moon as well, where we have a much larger range of plasma parameters that can introduce new complexities. And the reason that there's such a large range of plasma parameters is because the moon orbits through various regions of Earth's magnetosphere and then also out into the flowing solar wind. So the magnetotail lobes and the plasma sheet are the more high energy sparse regions, more similar to what we've seen in GEO. And I'll be focusing on the solar wind and magnetosheath regions. So these are more low energy, more dense plasmas. And so what can happen is that we have new formations around spacecraft that we haven't really had to deal with before. The first of which are spacecraft wakes. So in mesothermal plasma, the velocity of the electrons is faster than the velocity of the spacecraft, which is faster than the velocity of the ions. So as a spacecraft is flowing through plasma, it will knock the ambient electrons and ions out of the way. Since the electrons are faster, they can catch back up. They continue impacting on all sides. But since the ions are slower, they take several spacecraft lengths to catch back up and return the plasma to its undisturbed condition. So we get this, again, low density kind of net negative region on the wake side of the spacecraft. And it's also important to note that around the moon, the plasma is mainly flowing from the solar wind being emitted from the sun. This plasma has a bulk velocity at about 400 to 900 kilometers per second, whereas the spacecraft is only orbiting at maybe a kilometer per second. So these wakes are always forming on the eclipse side of the spacecraft. And we don't exactly know what these wakes are going to do to sensing. The thought is that that negative region may repel electrons and create barriers that make it more difficult, but we're not entirely sure. So we'll have to look into it. In addition, we can also get non-monotonic sheaths. So typically in this image in the top right, we have monotonic sheaths around a spacecraft. So you've got your different currents coming in, you've got your emissions coming out. So the secondary electrons and photoelectrons will typically just kind of leave the space. Or if the spacecraft is positive, they can be attracted back towards it and go right back into the spacecraft surface. Either way, the potential field is going to start at the spacecraft surface potential and then drop to zero as the distance increases from the spacecraft. But if the ratio of our emitted electrons to incoming electrons is large enough, and if our spacecraft size is comparable to the Debye length, so the Debye length is a measure of how far a charge's electrostatic effect persists in a plasma. It'll be about 10 to 20 meters in the environments I'm looking at here. But if we meet those two requirements, we can get non-monotonic sheaths. So in this case, right, we again have our currents coming in, but now the secondary electron and photoelectron emissions, instead of kind of leaving our space, will settle somewhere near the spacecraft surface. So since we've got a large region of electrons in one space, the potential field in that region will actually be negative. So the potential field will start at the spacecraft surface potential, drop to some negative value where those electrons have settled, and then start to plateau towards zero. What this can do is basically restrict further emissions from leaving the target. So, right, the emissions will go, they'll see that negative wall, be repelled from it, and go back into the spacecraft surface. So if the electrons can never leave the target, they can't reach the surfacer, and we can't do touchless potential sensing. So first, I want to determine the conditions in which these non-monotonic sheaths or this waste might create barriers. Exactly what impact this does have on sensing, if there's maybe something I'm not thinking about that could help us. And then where we should position our servicer with respect to the target to either mitigate or take advantage of these formations that I've just discussed. This first one will be looked into using a single spacecraft, and then the next two goals are investigated using both a servicer and a target in the simulations. Now, I use Nascap-2k and SPIS to investigate this. These are both spacecraft plasma interaction codes. Nascap-2k is America's, SPIS is Europe's. They've got some differences in setup, but for the sake of time, and because SPIS actually ended up being better at capturing these formations, I'll just be presenting results in SPIS. If you're interested in the Nascap-2k results, you can come chat with me, or you can reference my paper. All right, so first, this is the single spacecraft on the sunlit side of the moon. So we're in the solar wind. The Debye length is about 10 meters, 10.1 actually. And then we'll first look at this plot on the left. So here I've got spacecrafts of varying widths, and then the potential field along the x-axis about that spacecraft. So the left side of this plot would be the potential field on the wake. The right side would be the potential field where those photoelectrons are being emitted. And we can see that on the right, we start seeing a barrier from the photoelectron emissions when the spacecraft is about 8 meters big, so about 0.8 times the Debye length. But on the left, we start seeing that potential field drop negative and stay there when the spacecraft is about 6 meters, so only about 0.6 times the Debye length. So that means we'll have to start worrying about barriers when the spacecraft is right over half the size of the Debye length. And then on the right, we can see what this actually does to the currents being emitted, right? So that red line are photo emissions, or sorry, so this is the fraction of electron emissions being recollected. So that red line is the photo emissions. So you can see that more and more photo emissions are being recollected as the spacecraft gets bigger, right? This is because that barrier is getting to be more and more extreme. And then the other colors would be the secondary electron emissions. So all of the secondary electron emissions are always being recollected in the wake. So we're probably not going to want to put our spacecraft in the wake of the target. And then those two blue lines are on the side and on the RAM side of the spacecraft. So either one might be a better spot to put our servicer. And then here are just some images so you can actually see what's happening. On the left, we've got that smaller spacecraft, so no barriers. On the right, it's the bigger one, so you can see the barriers forming. You can see the potential field on the top. It's pretty monotonic about that smaller spacecraft. And on the right, you've got that negative region in the wake and where those photoelectrons have settled. And then on the bottom with a smaller spacecraft, because there are no barriers, the photoelectrons can kind of surround the entire spacecraft. Whereas on the right, we've got a big region near that wake where photoelectrons just can't reach. All right, so now kind of going through this process again, but with the spacecraft in eclipse. So right on the eclipse side of the moon. So the barriers in this region would not be formed from photoelectrons because the spacecraft is not sunlit. So it would be formed from secondary electron emissions. So initially, my material properties did not have the secondary electrons, did not result in enough secondary electrons being emitted to create barriers. That's this plot on the left. So you can see no barriers around the spacecraft, regardless of size. That's great. But if I increase the secondary electron yield for the spacecraft, then those electrons are large enough to actually settle and make a difference in the potential field, and we start seeing barrier formations in this plot in the middle. So here, we start seeing barriers both on the wake and on the RAM side when the spacecraft is about 6 meters. And in this region, the Debye length is 20 meters big. So that's right under a third the size of the Debye length. But again, in this plot on the right, we see that the secondary electron current emission is lowest on the wake side, right? So it seems that barriers may be an issue when the spacecraft is as small as about a third of the Dubai length, and we probably want to avoid putting our servicer in the target's wake. Here's the images again, right? On the left, you've got no barrier, so you can see the more monotonic sheath, and the secondary electrons are just leaving the spacecraft, whereas on the right, we've got that barrier on the wake and that like negative region kind of surrounding the spacecraft. And then the secondary electron emissions, since they can't just leave, actually kind of end up surrounding our target in that bottom right picture there. All right, so now I've characterized this for a single spacecraft. Now I want to look into simulations with both the servicer and the target present. So there are 4 scenarios. All right, sunlit with and without a barrier, eclipse with and without a barrier, and eclipse with and without a barrier. And then in each of these scenarios, the servicer and target are set to the same width. The servicer is held at 300 volts, and the target is just going to charge to whatever it'll naturally charge to. And then I'll use 3 relative positions. So servicer in the target's wake, target in the servicer's wake, and then both wakes parallel or both sunlit if they're in a sunlit environment. All right, so these are for simulations in sunlit environment. So regardless of if a barrier would initially form around the target or not, the maximum current is detected when neither spacecraft are in a wake. And then there's actually no current detected when the target is in the servicer's wake. And this is because the target is charging very negatively because it's eclipsed. It's not emitting photoelectrons. And also because it's in the servicer's wake, it's in that region where there are a lot of electrons surrounding it. So it charges very negatively, actually to the point where it's repelling most of those electrons. So if the ambient electrons can't impact the target, they can't cause secondary electrons to be emitted. So there's nothing to sense. And again, these are just some images so you can see what's happening. I actually found that the barriers just disappear when the very positive servicer is placed near the target. So this is good. It's kind of able to just punch through and attract those electrons out towards it, which is a good thing for our passive potential sensing. All right, and then here are the results in the eclipse environment. So again, we see that regardless of if there was initially a barrier or not, the maximum current is detected when neither spacecraft are in a wake. It's actually very close to when the wakes are parallel versus when the servicer is in the wake of the target. So either one would be viable options. And then the smallest current detected is when the target is in the servicer's wake once again, because it's charging negatively and repelling those ambient electrons. Here are some images. Again, the barrier just disappears around the target when we put that positive servicer real near it. And we can see that there are very similar trajectories, both when there was initially a barrier on the target and when there was not. All right, so I found that barriers can occur due to both non-monotonic sheaths and spacecraft wakes when the spacecraft is as small as a third of the Dubai length. And the ideal servicer position would probably be when neither spacecraft is in a wake. So keep those wakes parallel between the servicer and the target. And a highly positive servicer is actually able to overcome whatever barrier formations that I was able to model. Future work would be to just better characterize this, maybe test more spacecraft potentials and see if things change once we're dealing with smaller or larger potentials on those spacecraft surfaces. Thank you.